In this example, you are asked to calculate the Thevenin's equivalent circuit about terminals A and B. This case is very important because the circuit contains a dependent source. Most of the time, students are very comfortable in working Thevenin circuit problems when the circuit is a resistive circuit. Of course, this case is designed to challenge that and essentially ensure that you can handle circuits that contain dependent sources. Now, anytime you hear Thevenin equivalent circuit, you should already see the model for that circuit. And the model is a independent voltage source in series with a resistor. The value of the independent source is VOC, which stands for the open circuit voltage across those terminals A and B, and the Thevenin resistance is RTH, which we'll calculate also looking into terminals A and B. So those two steps essentially constitute the solution to the problem. Let's begin with the calculation of the open circuit voltage VOC. Essentially, VOC is just that, the open circuit voltage across A and B. It is really at your choice whether you decide to use mesh or nodal. Here I decide to use mesh, but you could have picked nodal depending on the problem. At this point, we're going to go to the steps a lot quicker, assuming that you're fairly comfortable in working out a mesh or a nodal procedure. So by setting up the mesh approach here, I've essentially come up with 3 finite meshes with mesh currents. I put voltage labels and polarities on all the resistors that do not have labels. And VOC, of course, is the voltage across the 2 ohm resistor, which I'm seeking to calculate. So at this point, this problem is a very typical problem using mesh analysis. So we're going to go to the typical steps. First thing I do is to write, of course, we have 2 current sources, so we're going to be writing the current sources in terms of the mesh currents. For the 5 amp independent sources, we have I2 minus I1 equal 5 amps. And for the dependent source, we have I2 minus I3 equal to 4 VA. So, and we know that for mesh, if we have 10 current sources, we are automatically going to get 10 equations, 1 per current source. So that's the first thing we typically do. So we have 2 equations. We need 1 more. Where is it going to come from? It's going to come from the super mesh. Now, in doing the super mesh here, this is an interesting case because we don't have actually a single mesh without current sources. All the 3 meshes have current sources in them. So we don't have any regular meshes without current sources. Now, we also have a case where the super mesh comes from all 3 meshes, not only just 2. So we take the super mesh as essentially merging mesh I1, I2, and I3, somewhat removing or ignoring, not removing, the branches that contain the current sources. What we end up getting is a mesh that is the larger loop of the circuit, which is highlighted here in green. And of course, we do the KVL equation, the Kirchhoff voltage law, which gives us the equation at the bottom of the screen. So I think this case is a nice case because in this case, you don't have a regular mesh, and you really have just 2 equations that come from the sources and a super mesh KVL. That it really is just all 3 of them, all 3 meshes. Next step, of course, is to use Ohm's law equations to write all voltages. And of course, we have to write VA as well. But for the voltages across the resistors, we use Ohm's law to write them in terms of the mesh currents. In this case, there is nothing extravagant about that, except we always have to be careful about the passive sign convention, particularly when we have resistors that belong to 2 meshes. In the case, for example, of the 6 ohm resistor, we have to say V1 is equal to 6 times I3, which enters the positive terminal, minus I1, which enters the negative terminal. And the rest is pretty much straightforward. VA is a little tricky here because VA is the voltage across the 5 amps. Folks, there is no Ohm's law for sources. There's only Ohm's law for resistors, so you have to find a way to express VA in terms of the mesh current. So what do we do here? I simply write VA in terms of V1 and VOC by doing a KVL in mesh I1. And once I do that, of course, then I can write it in terms of mesh currents I1, I2, and I3. Of course, using all these equations in the source and the KVL equations, then we come up with our typical three equations, three unknowns, the unknowns being I1, I2, and I3, and they are here at the bottom of the sum. Of course, we solve for the mesh currents. And once we get mesh current I1, actually, which is the one that we really need, we can go straight forward and calculate VOC, which is minus 2 times I1. And half of the problem is solved. This is really, the Thevenin problem is a two-part solution. And when I grade your problems, that's how I look at it. I look at the calculation of VOC at about half the points, and that of the Thevenin resistance as basically half the points. Now we're going to focus on how do we calculate the Thevenin equivalent resistance when we have dependent source present. Now, you can also have a circuit where you don't have a dependent source in it, but you're not able to combine the resistors because they're neither in series or in parallels. So you have to use a technique that I'm going to essentially outline here, even though the circuit may not have a dependent source. But in this case, it's a dependent source, so what do we do? Folks, there are three ways we can handle the calculation of the Thevenin resistance. I'm going to cover all three. Of course, in your case, you only have to select one. But I think it's important to know all three approaches. It's going to really give you confidence that you can do this. The first case here, which is outlined here, is by somewhat doing a half Thevenin and a half Norton. By saying half, we've calculated VOC by doing half Thevenin, and then we go back and we solve the same circuit. You notice that I put the same circuit with all of the resistors, dependent sources, independent sources in there. Nothing changed except we short the A and B terminals. In other words, you physically put a wire in there. Don't do it psychologically or mentally. We have to physically put it because that changes the circuit significantly by sticking a wire from A to B. So we stick in a wire from A to B. We solve that circuit, which is slightly different from the one that you started with, and then we calculate the current that goes from A to B, which I call here ISC, standing for I short circuit. Once we know that, once we calculate ISC, then the Thevenin resistance is simply the VOC that we found in the previous step divided by ISC that we just calculated. That is a valid option. This is by far the most common that you'll find in textbook. And it's a good one in some rare occasion. And assuming that at some point we may have an ISC that goes to 0, this thing won't work. So the other two, you need to know them as well. If we apply this particular method, in other words, we short circuit A and B, which you see I physically put the wire in there, and my goal is to calculate ISC. Now here what I'm doing here is working out a nodal procedure to show you how to use nodal to solve that problem. Now here again, there's an interesting case. You do not have to use mesh because we use mesh to calculate VOC. Every segment, every part of this problem, you can use whatever method you want. Here I decided to use nodal because I'll show you one of the pitfalls that happen when you use nodal in this case. Now, what we do here, essentially, we just stick in a wire between A and B. I want to use nodal, but by connecting A to B, I end up having a huge node, which I call V3 here, which starts from the 4 ohm resistor, wraps around, and go all the way around to the 1 ohm down there, or to the right. Now, you also can notice that by short-circuiting A and B, that the 2 ohm essentially is short-circuit, so physically you could actually remove the 2 ohms. It doesn't make a difference. But even if you didn't notice that, you could still solve the problem. What you really have to notice is that that node V3 is a very large node, wrapping around a lot of places. Most of the time, students connect A to B through a wire that still assume that they're 2 different nodes, and that's a fatal mistake here. Other things that I do, I select a reference node, which is at the negative terminal of my 8-volt source. By doing that, I automatically will know the value of V1. That simplifies my problem, and I will only have 2 unknowns, V2 and V3. After that, it's the standard, very standard node analysis problem with 2 unknown, V2 and V3. Calculate I short circuit. which is 2.768, and I can calculate the Thevenin resistance by simply doing the ratio of VOC to I short circuit, and I find 1.2 ohms. This is a valid way to calculate the Thevenin resistance. Next, I'm going to show you two other options which are equally important. The second option is taking the circuit and turning off all independent sources. You can see I put the X's, red X's, on both the independent voltage source and on the independent current source. Now, folks, you have to remember what happened when we turn off an independent voltage source. It's a short circuit. An independent current source, when it is turned off, it's an open circuit. In essence, you just take it out of the circuit and you leave the hole. What we don't do here is touch the dependent sources. The dependent sources remain in the circuit. That's why you still see them here. This approach, I like it a lot because, in essence, that's what you do if you take an ohm meter and measure the resistance of a circuit. If you had a circuit that was connected, you essentially take it out or disconnect it from the electrical outlet. By doing that, you're turning off all independent sources. Then you go in and stick in the ohm meters. Well, what does the ohm meter do? The ohm meter essentially sends a current and looks at the response of the circuit. So here what we do essentially, we say let's stick in a 1 amp current into the circuit and then use mesh or nodal to calculate the voltage across it, which I call here Vk. Now the Thevenin resistance must be Vk divided by the 1 amp. In the circuit that we're doing, this is what we're going to get. Now, realize that I had turned off the current source, the 5 amp current source. That's where that VA is. So you see there's a hole there because I essentially took it out of the circuit. And then I also turn off the 8 volt source, which turned into a short circuit. And then I go back now and stick in my own 1 amp source between A and B, and my goal is to calculate the voltage Vk across it. And I go ahead and do a straight mesh approach to that. There is nothing different from the first problem that we solved, except this is not the same circuit. It is very similar in nature, and the level of difficulty for solving it is very, very much common to what you just did in the first step. But the circuit is not the same. You do have to resolve it, redo the mesh equations and what have you. And then here I calculate mesh I1, I2, and I3. And then once I get mesh I1, I can calculate Vk, which is minus 2I1, and Vk is equal to the Thevenin resistance. And you notice that I got the same answer. Of course, you expect that I get the same answer that we got doing it we're using option 1. Solving these problems using option 2 or option 1, it is not difficult. What students often forget is they get to the step of finding the Thevenin resistance and they don't know what to do. That's what I want to show you. All 3 options somewhat worked out. In the last option, we also turn off all independent sources. That's why you see the X again, the red X on the independent voltage and current sources. But instead of using a 1 amp current source, we use a 1 volt voltage source. And we calculate the current I sub k that it puts out to the circuit. So this is actually very comparable to what we just did, except using a voltage source instead of a current source. Now, the question is, well, why use a 1 amp instead of a 1 volt? Which one is better? Which is a typical question that I get from students. You should really look at the method that you're using. For example, if I'm using a mesh analysis method, I like to stick in the 1 amp because that makes my solution typically easier, assuming that you can handle current source using mesh, which you are expected to. Similarly, if I'm about to use nodal, I probably will stick in a 1 volt because automatically that gives me a simple equation about the voltage source. Nevertheless, the Thevenin resistance is the 1 volt source divided by the current that it puts out, IK. Now, you have in this case, just like in the previous case, you have to turn off the independent sources. You can't leave them on. You only leave them on in the first option, which you're doing the half Thevenin and the half Norton. In this particular, using this particular option, We see the 1 volt source here. I have turned off the other 2 independent sources, but I don't touch. The dependent source remains at all time in the circuit. And then again, I go ahead and solve using mesh analysis for I1, I2, and I3. What I'm seeking is the current IK, which is the current going through the 1 volt source. So the current IK is equal to I2 minus I1. So once I solve my mesh problem, I get the value for IK, and then automatically the Thevenin resistance is just 1 volt divided by IK. And of course, I get the same answer that I got in option 2 and 3. This example wraps up the 3 options in terms of finding the Thevenin resistance if you have a dependent source present in the circuit. The no-no here is that you never turn off the dependent source. No matter what's the circumstance, the dependent source, you don't turn it off. You have to use typically one of those 3 methods, the first one being a half Thevenin, half Norton, that is doing VOC and I short circuit. The second one being you use an external current source to drive the circuit, but you turn off all independent sources in the circuit. And the last option being use an external 1 volt voltage source to drive the circuit, but you turn off all independent sources in the circuit.